make a short introduction of Uwe. So our speaker today is Uwe Ehret from KIT University in Germany. His presentation title is Using Information Theory for System Characterizations and to Analyze Learning. So without further ado, thanks Uwe, and the floor is all yours.
Thank you, Leila. So I'm going to present a few applications of how I use methods and concepts from information theory. And for system characterization, I'll present some aspects and to analyze the learning, so training models, basically. So I'll quickly jump over the key concepts because you're all aware of them. I'll just briefly show you the ones that we will use later on. Then I'll give you a brief overview on the playground, the model and the system I use. And then I'll show you the two applications for system characterization and for learning. So the key concept, of course, you're aware of is that entropy is expected information. And because it's a measure of the spread outness of a distribution, we can consider it a measure of data intrinsic uncertainty. Yeah. So if you're given only the distribution, how uncertain are you about a particular random draw from this distribution? And you know that the uniform distribution is for a discrete distribution, the one that maximizes uncertainty or entropy. So we have an upper bound for a given number of distinguishable states for uncertainty. And the lower bound, of course, is 0 if you have a Dirac distribution as the one shown in the middle. And for anything in between, you're somewhere between the log n and the 0 bits of uncertainty. Then because we can interpret information as the number of questions, the number of binary questions we are spared from asking if someone reveals a particular outcome of a random experiment to us, we can interpret it as number of questions that we either have to ask or are spared from asking. And this, for me, establishes a nice link between information theory and its interpretation and, say, some machine learning techniques like growing trees and using decision trees for classification and for prediction. Now, entropy is the uncertainty if we use an optimal questioning tree that we derived from the data themselves. Now, what happens if we apply a questioning scheme that still in the end will reveal to us all the outcomes, but that is not optimal? Optimal questioning schemes are those that at each level of the questioning divide the probability space into equal-sized halves. So you always discard 50% of your uncertainty. If we play this questioning game with the suboptimal questioning tree, and this is what we could call a model, because it's not the model or the questioning scheme derived from the data, then we will pay with additional questions compared to the optimal questioning scheme. This number of additional questions can be measured by Kullback-Leibler divergence. So you can see here compared to the calculation of entropy, we have here the probability of, according to the model that we're using, instead of the true probability of a certain outcome. But the expectation, of course, the summing up is done with the true probability of the outcomes. Unless we use the optimal questioning scheme, using a model will increase the number of questions on average, maybe not for a particular outcome, but on average. And we can use Kullback-Leibler divergence to measure exactly this additional uncertainty due to using a model, which is nice because we can treat in the same units uncertainty due to data intrinsic variability and uncertainty coming from it, and the uncertainty coming from the model. So Kullback-Leibler divergence is useful because it is sensitive to offsets both in position and spread of the distribution that we're seeking. So if you look at this example here, let's say the blue distribution is the true one, and our model distribution that we use to construct our questioning tree is the red one. Then we are both off. Yeah, we have a bias, and we also don't have the same spread. And if you look here on the right side plot, this is the, say, variations, the offsets in variance and the bias that are introduced for many distributions. And this is the Kullback-Leibler surface. It will be 0 and only then 0. Yes, Hoshin?
Finish your thought, and I have a question.
Okay. So Kullback-Leibler will be only then 0 when the two distributions perfectly agree, but you can see it is very sensitive to offsets in the mean, and it is also, but not in the same degree, sensitive to offsets in the variance. And if the truth should happen to be a Dirac, then Kullback-Leibler divergence is simply the log likelihood of the data. You can also interpret the mean Kullback-Leibler divergence of a distribution against all its individual measurements that make up the distribution. This will be the same value as entropy. So entropy can be interpreted as if you use the data distribution as a model and you want to guess the individual values, that's your model-derived uncertainty, which is also, I think, a nice interpretation if you look at the data that make up your distribution. One problem yeah, Hoshin?
Sorry, are you saying that's the KL divergence between the distribution and the mean as a delta function?
It is, let's suppose you have a data set of 100 data, and you have the distribution from these 100 data points. If this is your model, the distribution, and now you want to guess every single value, which is a Dirac then the mean uncertainty over all these 100 points is exactly your entropy. So it's the distance between 100 Dirac points and your model, the data distribution.
Okay, can I ask my other question? So I notice your plot varies the mean from 0 to 2 and sigma from 1 to 2. Have you played this out further? Because I checked with the Jensen-Shannon divergence and it saturates, right? So does the KL divergence also become a constant after if the two distributions are far enough apart?
It will actually jump to infinity if the two, if it's distributions that have a particular value range and they are off, completely off, then a Kullback-Leibler will move to infinity. So it's not saturating. Okay. But what you can see is that if you can somehow compensate an offset in the mean by an offset by increasing your model uncertainty, this will lead to lower Kullback-Leibler divergence than if you have a narrow predictive model and it's off. So if you're off, you better be vague in your answers. That's the interpretation. Okay, and of course, we'll have to handle this problem if the probability of a certain event in real is non-zero, but your model says it's 0, we will have to handle infinite Kullback-Leibler divergence, which then completely spoils, say, a measure of distance. So these are the three, or basically the two main things, entropy and Kullback-Leibler divergence, that I'll need in the next slides. My playground, still coming from the chaos research group that we had from 2011 to 2019, is the Attert Basin in Western Luxembourg. It's 250 square kilometers in size. And it's a typical midland catchment with some snow influence and quite pronounced floods. And the toy model that I'm using here is a simple HBV model, like a water balance model, conceptual and lumped. It has overall, as you can see, a typical bucket model, one bucket for surface runoff, one for interflow and base flow, and one unsaturated zone bucket for evapotranspiration and soil water storage. And its forcing consists of mainly rainfall and the other hydrometeorological or climate variables. Overall, it has 18 system variables, which is both state and flux properties, and all the corresponding parameters of the model. So overall, it's 24 variables. So if you like, the space in which the model states are placed is a 24-dimensional space. Yeah, if we take both the forcing and the model variables. For all further calculations that you'll see, I discretized the value range for each variable in only 4 bins. Yeah, the entire value range is represented or split up into 4 bins. So we have a rather crude subdivision of each value range into, say, low, mid-low, mid-high, and high, something like this. And now we're going to use this, say, 6-year runs of the model for several purposes. The first is system characterization. And I want to show you a few ways to characterize the system in terms of uncertainty, predictive uncertainty, complexity, and we're going to look at what certainty or uncertainty subsystems add. When I'm not talking about subsystems, but about the system, it's always the 14-dimensional variable space. So let's start from the certain aspects. If we know each variable value and its position in time in advance, then our uncertainty, of course, is its minimum, it's 0 bit. Yeah? That means I have full knowledge of all the data and where they go. The other bound that we can use is if only the value ranges for each of the variables are known, and I assume, because I have no prior other knowledge, a maximum entropy uniform distribution, then I know my uncertainty is log 2 of the number of bins. And because now we have 4 bins for each variables, and we have 24 variables, we have 4 to the power of 24 possible individual system states, which is quite a lot. But due to the logarithm, the uncertainty, if we just know the value bounds and the dimensionality, is 48-bit. So this is the worst that can happen, and that's our, actually it's not the worst. We could be much worse off if we have a poor model for prediction. This would be our best default model and our lower benchmark for model performance. Fortunately, our system doesn't really move or doesn't really visit the entire state space of all variables. It's usually confined to a relatively small region. Here you can see one subset of the state space comprised of only 3 state variables of the base flow, the interflow, and the unsaturated zone storage. And you can see here, this is the trajectory and the subset of the space where the system actually can be found in. And this, of course, will, if we know the data in advance, reduce uncertainty. So if we know each variable distribution and we treat them individually, not jointly, our overall uncertainty is the sum of the individual entropies of each of the variables, which for our case is 10.7 bit. But we know more than that because we know these variables vary jointly. So if we calculate the joint entropy of the 24-dimensional distribution, our uncertainty is actually 7.2 bit. So this is considerably less than our benchmark maximum entropy uncertainty. And this is now again a benchmark against which a model should compete. This involves, of course, calculating entropies of 24-dimensional distributions. And it's very useful in that context to use sparse matrix operations. And then it works quite nicely. If not, you get a problem. So that was basically just a brief way to use information measures to characterize systems in terms of their uncertainty. Now I would like to show you one other way, one other aspect of systems that could be of interest, complexity.
Sorry,
and this is basic. Yes?
Sorry, could you just go back one slide?
This one?
Yes. So can you just give me the intuition on what the 7.2 bits means now?
Yeah, okay. Let's suppose we only work with 3 variables. This space here is then along each axis split up into 4 bins. So altogether, this will be cubes of 4 times 4 times 4. Yeah. And in this cube, in this Minecraft world, I place my observations of the 3 system states. Yeah. So I lose their time order. I just take the joint distribution. And then I calculate the entropy of this 3-dimensional distribution. Mm-hmm. And the value you saw is not for the 3-dimensional, but for the 24-dimensional distribution. That's this here.
So that's the best you can possibly do if you're just, if all you have to do is predict in which box the system output is.
Exactly. So I threw away from the data points their position in time. I made them, you know, I made a distribution out of them, but the joint distribution of all the variables. So if you'd ask me what is for a particular point in time, the state of the system, what are the values for discharge, rainfall, and so on average, I'd have to ask 7.2 questions to guess that. Using
so it could be in any of these boxes, and to resolve which box it's in, I would have to ask that many questions. Okay.
And actually, it's quite interesting that you only need 7.2 questions to identify one data point in a 24-dimensional space. It's not much. Stephen?
Yeah, I have one. I'm not sure exactly what these sparse matrix operations are, but in general, if the end result is purely bin counting, then typically there's a problem with just the sparseness of the data points in this 24-dimensional space. So I think this 7.2 bit might be very much underestimating the true information content. For example, if you think how many data points you put in there, the maximum entropy you can ever get by placing those data points in these 2 to the power 48 bins that you have, if none of the bins contain 2 observations, that's the maximum joint entropy you'll ever get. So that would be the log of the number of data points, basically. So as long as
and that was something like 64,000 or so time steps.
But he's assuming that assuming that as long as you get it within one of the 4 sections, that's correct. I mean, this is a discretization down to 4 in each dimension.
But it's a good comment by Stephen, because what I assume is that the data I have from the 6-year 1-hour resolution model run is a virtual reality and represents the truth. Of course, it will never be able to fully populate the 24-dimensional space due to the limitedness of the data, but I assume that's the population, basically.
But what's 2 to the power of 48? I think it's a lot more than 64,000, right? So even if it's a virtual reality, I think just numerically you're never going to get above. Well, you'll get above 7.2 bits, but not much more.
Yeah, the 48-bit are the theoretical maximum if you would have really a uniform distribution populating the entire state space.
Yes, but if you have limited samples, even if the true process were uniformly distributed, you would never get your samples uniform. Oh, what is it? Yeah, exactly. That's a bit more than how Sheen is showing the number. So I think, yeah, I'm just saying that's something to watch out for.
That's actually a good point, and another limit, say, we could place here in this list to say, but actually because of the limitedness of the data, you could never, the maximum is lower and a function of the number of the data.
Yeah, it's log 2 of the number of data points.
Mm-hmm.
So
something interesting that I have
bits.
been playing with something very similar, because I trained 3 models in Chile with 322 catchment, and I was calculating the entropy for all the predictions, and the maximum value that I can have for the entropy is almost 5 nat. That is exactly 7.2 bits.
No way.
Yes.
Were you working with uttered data?
It's a camel CL. It's the same like camel from here, but it's from Chile. So because this was my thesis, I did this. I create a GR4J model and random forest and LSTM model in all the entire data set. So now, given that I have the data, I can quantify the entropy. This is what I'm doing now. Mm-hmm. And the value that I have is exactly that.
Okay, it would be a very high coincidence if we would use the same binning scheme, and the same number of variables. I'm just wondering whether the hydroclimate is similar and whether this could be a reason that the overall uncertainty of these variables jointly considered comes down to similar values. We should talk about this in detail afterwards.
Can I ask a quick question, Uwe?
Sure.
Can you go to the previous slide before this one? So I'm trying to understand the sparseness, and are you identifying this 4 discretization in 4 compartments, 4 ranges, based on data or based on some prior knowledge? Because if it's based on data, then shouldn't we get some values in each of those 4 compartments? Because you're trying to set the range from the minimum to the maximum and based on data. So there is a data which should fall into every box. So I don't understand the 0 values in those boxes.
You mean in this particular slide?
I mean, I'm using this as an example. So if you have 3 variables and you're setting the range from, say, 0 to 2.2 for SU and 0 to 0.03 for SI, that is based on simulation data. And within that, you're categorizing it as low, mid-high, and high. So you already have this data points. And so how would you get nothing in that low and low category for 3 variables?
Okay, so the value ranges are derived both from the data plus, say, physical considerations. If in the model you reach never a storage fill level of 0, I would still place the minimum at the physically possible lower limit of 0. So this here is not the entire time series, so it's easier to see. It could still go towards smaller values. And then secondly, the value range is not entirely derived from the data only.
Okay.
Okay, Should I go on? Okay, so here's another aspect of how we could characterize systems, complexity, and this way I treat and see complexity is inspired by Jakov Pachebski and Holger Lange and the work of Michael Haus. So you will see some similarities in that in what they are doing. For me, the definition of complexity is very loosely the uncertainty we have about the uncertainty of the system. Yeah. You could have a chaotic system where uncertainty is always high, but it's always at the same level, very high. You could have a very boring system where uncertainty is always low, but always low. So your uncertainty about the uncertainty of the next time step is also low. And you could have systems where the system changes between, say, periods or states of high predictability and low predictability or uncertainty. And this is then what I would call a complex system. So what I will show on the next slides is the approach I use only for a one-dimensional data set, discharge simulations of the catchment, but the values I'll show are always for the joint 24-dimensional data set. So the idea is very simple. Uncertainty, or I subdivide the data, time series, could also be a spatial series, into blocks. Yeah? Here it's just one block covering the entire data set. And then I calculate the entropy within that block. If I have more than one block, I calculate the entropy of each block and then say, get a measure of mean uncertainty as simply the mean value of these block entropies. Then my measure for complexity is from the set of entropies I have for each block, I calculate the entropy of these entropies, of the distribution of the entropies. And this is my measure for complexity. Now, of course, it's simple for a single block. But if you divide the data into two blocks, you already have something to calculate a mean of and something to calculate an entropy from. And then I just did that for more and more blocks until each point in time was in its own little block. And what we get from these joint calculations of mean entropy and entropy of entropies is a plot like this, the little blue line. But let's start with looking at the bounds first. On the x-axis, you see the uncertainty, which is expressed as the mean of the block entropies. Yeah? Here it says KLDs, Kullback-Leibler divergences, but it's block entropies. And of course, the maximum you could get is again the 48-bit. That would be our maximum for uncertainty, or something lower according to Stephen. Then the maximum complexity you could get would result from if all the block entropies are distributed according to a uniform distribution. And that's, of course, then also a matter of into how many discrete blocks do you subdivide the value range of the entropies. Here I used, I don't know, 32 or so bins, which would then be my upper bound for the maximum complexity of the data set. Now, my system actually being subdivided into only one block shows the normal system entropy of 7.2 bit. So that's the data subdivided into one block. And at the other end, when there are 16,384 blocks, one for each time step, my entropy is of course 0, because I know there's no distribution, no uncertainty within a block. And now the interesting part, of course, comes in the middle. Here you can see for a particular resolution of the data into blocks, there's a maximum of complexity, but still it's far away from the maximum complexity. So this could be, if you want a single measure of complexity, you could say I pick the complexity where it's at a maximum. This is a zoomed in version, which was here, whatever, 1 bit. And it was reached when you subdivide the data into 32 blocks, which means one block is 3 weeks. So that looks something like this, just to give you an idea. So it means the variability of within block distributions is highest if you use 3-week blocks. So there may be blocks then where uncertainty is very low, and others where uncertainty within the block is very high. Maybe we can relate this somehow to the hydroclimate, to some whatever, circulation patterns and vegetation patterns and so on. What I don't show here, but what you could do is compare this particular look that's very typical for a hydrological system to the same considerations for other systems like red noise or white noise or sinusoidal systems. And each of them has a very particular, say, set of trajectories through this space. So this could be a way to compare and to quantify the complexity of a system as another facet of system characterization.
This is done for streamflow, right? The one you're showing us?
No, this is done for the entire 24-dimensional data set. So it's always a block in a 4-dimensional space for which I calculate the entropies.
So this includes the precipitation and everything.
Everything, yeah. I'm just showing it for the discharge here to give you something to look at.
If you do that just for discharge, do you get a similar pattern or something different?
I tried once. I have a plot, but I don't know where it is right now. But typically environmental systems, that was also when Jakov Pachebski showed his slides, they were quite benign in terms of their complexity compared to some artificial, say, white noise processes or others. So there was some self-organization in the data.
I'm just curious, if you had a system driven by precipitation and resulting in streamflow, and if you did the complexity characterization for precipitation and you did it for streamflow, I'm curious how they would look different.
I remember that Jakov showed that, showing that either it's a filter, the system is a filter that reduces or increases complexity, and he also showed comparisons of natural systems and human-made systems. So this could be done here. The difference between what Pachebski and Lange and Haus did and what is shown here is that I use entropy now throughout. They used some other measures for complexity, but here we have the same units basically on the X and Y axis. So this and that. So we could also calculate some kind of relation between uncertainty and complexity if we want.
I'm also wondering, like I'm thinking as always in terms of compression. I'm wondering if you would use this block approach as an approach to compressing the data, then my guess would be that in decoding it, first you have to decide in which type of block you are. So that would cost you the entropy of the entropy number of bits. And then within the block, you can code it with the entropy. So basically the sum of the average entropy within the block and the entropy of entropies would be roughly the bit length per sample that you would be able to compress it to if you use this.
And yeah, exactly. You could also use, say, binning schemes, not the equal-sized blocks, but equal entropy blocks or something like this that don't result in different complexities for some binning, but use that as a pre-constraint. It's the same question as, do you use a variable bin width scheme for entropy calculation of a bin distribution, or do you keep the bin width fixed and then you calculate entropy from that?
No, that's a good analogy, because you would then expect that the bin widths would be very narrow when you have a lot of activity and wide when you have very little activity.
Yeah. In low flow cases, you could have one bin of a very wide time bin, and still the data would look the same within.
Yeah, that would be like similar to run length encoding, where if you have long runs of the same value, you just say in a compressed file, there's going to be 20 zeros now.
Yeah, it would be identical, because you'd be binning on the cumulative distribution as a uniform distribution. You'd be separating the bins, and when you put it down, it would tell you with that much loss of information, how wide a period would you just have a single value in?
Interesting.
So you're also not limited to, say, neighboring time binning or neighboring space binning. You could do that with space too. You can use any scheme if you like, whatever your preference is.
So at 3 weeks, you have maximum unpredictability between 1 week, 1 3-week block and
the next, exactly, yeah.
Okay.
Okay, so that was both considerations that treat the entire system as a block. Now let's briefly look at what is the contribution of subsystems. And what I did here is, for my same system, I simply start rattling on individual parts. It's just one or several of them. So I do random uniform perturbations, which is quite violent. Yeah, I replace the data points by a uniform distribution covering the entire data range. And this is a perturbation that I can, in a binning scheme, simply quantify in advance what the loss of certainty is. Yeah, if I replace a particular sequence of known values with a uniform distribution each, it's just the added uncertainty is a log 2 of the number of bins. So because I'm not comparing it to the data distribution, but I'm replacing each Dirac value with that distribution. So I know exactly my impact. And then what I do is I measure what the consequences of this perturbation on the entire system, on all other variables are, by feeding this perturbation through my virtual reality, through my model. So, and then I can compare, say, the cause, yeah, the magnitude of the cause and the magnitude of the effect. And if I like, I can compare, calculate a ratio of that. So if I calculate the ratio, say, of information loss due to the cause plus the information loss shown as the effect by the information loss of the cause, if it's smaller than 1, then it's dampening. Actually, it will never be smaller than 1. It will be, at most, it will be 1 at the smallest. But if it's much larger than 1, then this perturbation has some kind of an amplifying effect in the system. So what I did was, once replacing the temperature observations with random uniform or with uniform distributions. So the information I took away as a cause was exactly 2-bit. And overall, for all variables, the information loss was 7.6-bit. So the ratio is...
Is this
Sorry?
Monte Carlo simulations, or these are?
Yes, I just did many Monte Carlo simulations, but the problem is you need to run a lot of Monte Carlo simulations if you really want to truly sample this uniform distribution. It's not a problem if you vary a single variable, but it will become a problem if you vary 3 or 4 or 5 together. So then I varied the temperature and the month of the year, which governs vegetation and so on, jointly. So the cause was 4-bit information loss and the effect was 9.7. So Here it seems month of the year didn't change much. Yep, the joint effect was not really, say, amplifying. Then I changed the last variable, the output variable, the downstream variable of the system Q out, and as expected, the cause and the effect have exactly the same magnitude because this variable doesn't affect anything else in the system. So here I have a theoretical expectation for the effect, the magnitude of the effect, and it was also 2-bit, which could be a way to estimate or decide whether your Monte Carlo sample was large enough. Yeah, that's the theoretical limit you should reach.
Sorry,
Then,
sorry, were we missing something? Can you give us the intuitive interpretation of the ratio? Yeah.
Oh, it just measures what's the relation of the impact, the cause, and the effect on the system.
So it's cause plus effect over cause, right?
Yeah, let's say you have a sequence of domino stones. If you touch the first, they will all collapse. So the effect of your small cause, tipping a single one, is very large. If you tip the last one, your cause and the effect are equal. And if you tip no domino stone at all, but somewhere into the air, you have a cause, but you have no effect. So that would be the...
So your ratio is cause plus effect over cause.
Yeah.
So it had always greater than 1.
Mm-hmm.
And
because
so,
the effect calculation includes the cause, because it's also a system variable.
Right. So a large number means a strong effect relative to the cause. Okay.
A large ratio means a strong effect. And here you can see when I changed evapotranspiration, the cause was still only 2-bit, but the effect, the changing of all the other variables was huge. So it seems quite a, a tricky variable, which also means it may be good to measure this, this property.
Obviously, if you change precipitation, you will get a very large effect, right? So.
Mm-hmm. And here, your entire system could also explode. If you use rainfall from the entire possible value range, it's quite a mess. So I was wondering also whether I should really use random uniform perturbations or smaller perturbations of the system. Okay, then the last application I want to show is learning. And this is actually inspired by the work that Wei Gong did together with Gray and with Hoshin. The idea is simply we want to measure in a learning process the information contained in the data that we use for training a model, like the forcing and the evidence that we use, the information that's contained in the model hypothesis itself, and the amount of information that our training algorithm allowed the model to absorb information from the training data. If you have a poor training algorithm, it may not absorb any of the offered information. If it's a good one, it will absorb everything. And we can again measure this with Kullback-Leibler divergence. Here I use a very simple setting. I assume I know the entire system almost perfectly, all the parameters and the structure of the model, except this one retention constant value. And what I have for training is the observed meteorological forcing and this single discharge or this single system variable, the output. Yeah, that's what I have for training. And this is what I want to learn. So what I want to show you is basically a sequence of steps where I add more and more information to the problem and see how it reduces uncertainty. And uncertainty, again, is always measured by the Kullback-Leibler divergence of the true data, each data point in its beauty, and the predictive or the model distribution that comes from our untrained or trained model.
Still using 4 blocks per variable.
Exactly. Not more. So if I know nothing about the system, my uncertainty is basically infinite. Yeah, that's the starting point. The other end is if I know in advance all the forcing variables, time step by time step, all the system variables except the evidence, plus the evidence, the variables I have for training, then there's zero uncertainty. Yeah, and I don't even need the model because I have the data. So it's a perfect model, basically. Now, let's start from the other side. If I know only the value range for the forcing, the system variables, the variables I use as evidence, and I apply a maximum entropy model, then we'll see again, we're at this upper limit of 48 bits. Yeah, so coming from infinity, this is already quite a step. Then let's assume I'm now slowly adding the data that I have available for learning later on. Let's assume I know the forcing variables, but just the value ranges of the others. And again, I'm using a maximum entropy estimate for what I don't know. Then this means I added, I'm now 6 variables less uncertain. Yeah, so that reduces uncertainty by 12 bit. This is just from knowing the forcing, okay? Now I'm bypassing one step. I'll come back to that later. If I use the forcing and a prior model, as I said, my model is almost perfect, except this one parameter, KB. I only know a certain value range and I assume a uniform distribution. If I run this model in a Monte Carlo mode with the observed forcing, this is my uncertainty. So you can see my model is already almost perfect. It reduced uncertainty by 34 bit down to only this. Yeah, so just to show you that there's not much left to learn. Nevertheless, before I start training the model, I'm also adding the evidence. Yeah. So I'm again taking 2 bits away of the uncertainty about the entire system. So now I'm down to 34. And if I could perfectly train my model, I should come down to 0. So now I'm training the model and try to come from the maximum entropy estimate of my KB parameter to, if possible, a deterministic single valued. But in fact, it will be just a narrow distribution. And this is the result of learning. Moving from my prior model to the posterior with a better estimate of KB, I was able to remove further 1.23 bits. So I'm down to 0.6 bits of uncertainty now. The entire message of this procedure is that we can measure in the same units and in a similar setting the information that enters the problem through the forcing and the evidence, through a model hypothesis, and then how much information is captured by the training process itself. And that's what's left. The 0.6 bit are left because my training algorithm was not perfect. It could have, in principle, identified everything, but it didn't. Just because
your third column is the information added by the model structural hypothesis.
Exactly.
Okay.
And that included everything of the real virtual reality world except knowing this KB parameter. Yeah. If I would start from no model hypotheses or a very weak one, then this here would not go down that far.
So an interesting bar to put in there would be, you know the structure, but you have the parameters within all the parameters uncertain within some range.
Yeah.
It would be interesting to see that one. Yeah.
And this would have meant running many Monte Carlo or parameter hypotheses sets. That's why I started with one.
Okay.
And that's where the practical problems come in.
But you could do a kind of a bootstrap, and you could get an estimate with some bars on it or something.
And here it would be definitely good to talk with mathematicians and so on that can help on smart sampling of parameter spaces without overdoing things. So that's all. Thanks for listening.
Very interesting.
So where do you see yourself going, Uwe? You got three or four main concepts here, right?
Actually,
are you there?
yes, I'm waiting for you to continue.
So you got the concept. You're taking your system, and one aspect of this is to discretize the system and work in a discrete framework, because it allows you to use the log2 question method of quantification, right? So you're not working in continuous space, you're working in a discrete space. So that's one interesting thing. And then that allows you to use all these metrics like Kuhlberg-Leibler divergence, entropy, and so on. Then you introduce the concept of uncertainty and uncertainty of uncertainty as a measure of complexity. Then you introduce the concept of, did I miss something in between? Using this to quantify the information added by different kinds of information, by different kinds of the information added by different the uncertainty
by different subsets,
different kinds of information. Right? Yeah. Okay. Yeah. Okay. If I summarize that correctly, I'm not sure if I added everything. So I'm just curious where you see taking this analysis and trying to get the bigger picture. Yeah.
I think the goal is to be able in training and testing any kind of model to quantify where actually does the help come from, where does the information come from, and how can I quantify that on the way. And in principle, this should be possible for, not only for conceptual models, hydrological models, but for neural networks or anything. And the main reason I'm living in this Minecraft world of binned representations is because many estimates and many considerations and comparisons get very, very straightforward. And I don't introduce, except the binning scheme, I don't introduce much side information about particular shapes of distributions and so on. And so what I want to do is following information on its way through data and models and to optimize learning.
So I have a question for Stephen. When I first heard Uwe talk about this, what impressed me about this was related to the work you did earlier in your thesis, which had to do with quantifying prediction accuracy of forecasts and so on. You remember that?
Yeah.
And we tend to work in a continuous space, but in reality, once our forecast is within a certain distance of the observation, we're usually quite satisfied, right? So this has to do with the uncertainty externally imposed by the decision maker, right?
Yeah.
So I'm curious what your intuition is on that. Is as a forecaster, it's sort of like Keith Bevan's limits to acceptability. You're saying you come this close, and then I can say, okay, that's a perfect forecast for all practical purposes. That my model is good enough, right? Do you have some intuition as to what that is? Would it be dividing the stream flow or the variable up into 100 bins? Would it be putting a relative uncertainty size on every value? What would be the one that sort of lines up with your intuitive understanding how people might use that information?
I think it very much depends on the particular decision problem you are looking at. So basically, there's a difference between useful information, which you can maybe, it's not entirely quantified by information, but you would say you can quantify that by utility for a given decision problem. And then there's information in a pure sense, if you don't know anything about the decisions you're informing. So for example, like here in BC, we have a lot of run-of-the-river hydropower, and then you have to leave a certain amount in the stream as environmental flow, basically. So all they are interested in is, are they above that limit? Do they comply? So basically, it's a 1-bit piece of information that's tied to the decision problem. So I think what would be useful really depends from case to case based on the decision problem, and it's actually interesting to think about when we actually would want to maximize utility of a model and when we want to maximize information.
So the optimal binning would depend on the you're saying the optimal binning would depend on the utility function for that particular decision process.
Yes, but and in a way that's related to the what is the information about question, right? Because if you quantify information content, it's information content for a certain question. So if your binning basically sets up the question you're measuring the information relative to and the uncertainty. And then once you've done that, I think there's a couple of other things that influence utility, right? So information would be equal to utility if your decision problem is a horse race in which you can spread your money over different outcomes and you get a certain return based on fair odds, and then after that bet you get your money and you can reinvest it. In that case, utility and information are exactly the same. And that's what I argued in my thesis as well, that there's two main differences from a horse race for typical decision problems in water resources. One is it's not entirely, the loss function is not as local as in information, because like this infinite penalty, if you assign 0 probability to what actually happens, in reality, if you optimize your hydropower reservoir release for a certain inflow, but it was not the correct inflow, but you were like 1 bin off, even if you completely thought that was going to happen with 100% certainty and you optimized only for that, if something else happens, you're still quite optimal, because like you don't, like if you bet on the horse with the next number from the one that won, then you lose all your money. If you bet on the wrong inflow in the next bin, you're still quite optimal. So that's one difference. And the other is that it's not completely sequential, because like you don't put all your value in each time step. Like with the horse race, if you bet your entire capital in each race,
it's a dynamic programming problem.
You have a chance to lose it all, and then you cannot continue and you can never recover from that. Well, with a reservoir operation, if you make a wrong decision in one time step, you have some new water coming in the next time step that you can allocate, and maybe you do a bit better. So
I guess I was just seeing a practical application of what you're doing, Uwe, in some kind of a decision context.
And I have to agree with Stephen. I had problems when I tried to find from a set of old situations, or from a library of situations in a hydrological system, and I wanted to find those that are similar to the current situation. I also used a binning-based comparison, and I got the problem that I was discarding old similar situations if they were just one bin off, or quite close. So that is not the horse racing problem, but the water management problem. And at this particular point, I also started to move towards comparing with something like a maximum tolerable distance between the current situation and the old ones, because the binning approach was too strict. If you didn't hit the correct bin, if you're close or far, it was wrong. That was too harsh.
Yeah, and I guess the alternative to that, if you want to stay in the information framework, is to kind of smear out your probability a little bit, because then
use Gaussians,
yeah. So maybe using kernel density estimation or something.
Interesting.
So then you also get this being in the next bin not being completely wrong, because instead of putting the observation in just one bin, you kind of smear it out a bit. Yeah, very interesting. Those are the type of questions I've been thinking about a lot as well.
I guess what strikes me is that there's this interesting. We tend to, when we go to school, we tend to be taught to think in terms of continuous functions and continuous spaces. The calculations are much simpler, but of course, you need, as we know, huge amounts of simulations when you go into a discrete space. But I tend to think that when we operate in the real world, we think something closer to a discrete space representation, because we're never concerned about things being perfect. We just care about things being close enough, right? So there's some power to being able to do this approximation sufficiently well. And then the question is, what is sufficiently well, right? How do we characterize a world in such a way that when we do our calculations, they're sufficiently good?
Yeah, and I guess for things like audio compression, that's often related to what you can still hear. Right, so I think in MP3, like after a big hit on the cymbals, actually the quantization gets or the compression gets a bit less precise, because you cannot hear the small things after this big sound anyway. Right. So it's.
So I was thinking of flood forecasting. If you would make narrow bins near the flood levels, and you would make wider bins in the places where you don't really care whether your model is right or wrong, right? Something like that.
Yeah. Yeah, so that's definitely kind of the way to bring the about of the question into the consideration. Yeah, but
if you went from 4 to, I don't know, 100 bins, whatever it is, what is the practical implication? Because 100 bins is like saying 1%. I'm willing to accept a 1% tolerance.
I think it would still be possible from a computational point of view for my 24-dimensional space. But if you would use distributed models with more than one subcatchment, it could become a problem. In principle, nothing changes. It will just become a computational problem. Well, just in
You would have to design in such a way that you only look
I mean,
in bins close to where you already have trajectories or something like that, right?
actually, that's one thing I found out when I, was fiddling around with these numbers. Good thing is about the binning, I have the theoretical upper limits without, having to do a lot of computation. It's just a log to the power of something. And for the rest, I just have to consider the bins that are actually populated.
Yeah.
So the problem comes if I replace one dimension of space by a uniform distribution, and I have no closed form way to calculate its effect. The cause is always easy to calculate. It's 2-bit or 8-bit or whatever of information loss. But if I want to propagate this disturbance through the system, there's no other way than running the system model. And then the required sample to represent this distribution becomes high.
But you could sort your random perturbations in distance from the true value, whatever your nominal value, and then that would restrict the number of bins you have to search on because things would presumably move in a continuous fashion out from your current envelope somehow. Did that make sense?
I guess there are computationally smart ways to do that, but these ones I haven't found out yet. And so I'm still in the brute force mode.
Yeah, and I think like if you want to guarantee that if things are uniform that you can actually detect it, you should have as many samples as bins in your so maybe if the complexity is low, maybe smart algorithms can kind of search the space that's actually occupied, but in the worst case I just calculated with 100 bins in the 24-dimensional space, you would need 1 to the power of 48 bins. So that's the number of atoms on Earth, more or less, or half, to be honest, but still. So
still a lot.
It's a lot, I think.
I think this is where you have to start thinking in terms of kind of a Lagrangian framework. In other words, you have to move your coordinate system along the trajectory, and then as you add uncertainty, you're expanding out around that trajectory, right? I mean, you can't be thinking in terms of a 24-dimensional 100-thing space. You have to change your coordinate reference frame somehow.
And at this point, probably I also have to start restricting my perturbations not to a uniform distribution covering the entire physically feasible value range, but to something more realistic. But then my easy a priori calculation of the information loss due to the perturbation is lost again. So, it's not just then the logarithm of the number of bins along that axis.
Well, if you're using a Gaussian distribution, you just have to use the equation for Gaussian. So that's the standard deviation, and you get the entropy as a function of the standard deviation. So I don't think that's a problem necessarily.
But I'm really keen on further developing this perturbation idea. It also helps in what I haven't shown here, using any perturbed system state and then watching the system move towards equilibrium to calculate the distance from equilibrium of the system, which we could use in an analog way to, say, thermodynamic entropy in systems that are not primarily governed by physical laws. but I haven't shown that yet.
Here's what I think. Here's what I think the problem boils down to. It's something along the lines of you have a deterministic trajectory through n space, yeah. And if you did the mutual information of all those variables, you get a mutual information of 1, right? Because it's a deterministic trajectory, right? As you add uncertainty, you get a tube forming in that high dimensional space, right? The uncertainty tube. So what we need is a method for calculating the loss of mutual information as that tube expands, right? So that's again analogous to what I was saying earlier. We actually have to find a way to follow the coordinate system has to follow the axis of the tube in order to calculate that. Right?
It also means we may change the size of the ensemble depending on how uncertainty at a certain point in time develops. So I'm not using 100 Monte Carlo simulations from the top start to the end, but I'll vary that on the way.
Right. And
which could be a parsimonious way of estimating uncertainty.
So we know mutual information is h of x plus h of y minus h of x minus h of xy, right? So if we somehow change the coordinate system to follow the trajectory, then essentially what we're then just measuring is hxy, right? The uncertainty around that. And this, I think this is related to the problem that I was trying to talk to you about how we extend our method for calculating entropy to calculating mutual information. And I think the trick is you have to convert it back to a problem of calculating entropy. If you get the analogy, right? Because we're doing h of y minus h of y given x, which is a problem of calculating entropy. So how do we do that? And we have to find a trick which allows us to be able to do that in high dimensional spaces. Because then you might be able to do this without
lots of work.
Yeah, might be able to do this without using. Oh, your binning would be a different kind of a binning, which would be using I have to think about this, but
a tubing.
It would be a binning away from the the center trajectory, something like that. And then you wouldn't have these billions of bins to worry about. You would need only the number of bins necessary to characterize uncertainty, the precision level that you care about for your problem. Anyway, just waving my hands.
Again, the Minecraft analogy, they also don't show the entire block landscape. It's made up on the way as you move. So
yes.
Minecraft is the key to all.
We live in a Minecraft world. Oh, I'm going to have to send you this paper.
At least my sons do.
Actually, let me drag and drop this paper to you guys. I think, how do I do it? I just drag it onto the screen to share something.
I think you can share a link in the chat.
Yes, in the chat, there is a small cube that says file. I think you can click there and then you can upload it there.
So I go to chat.
Go to the chat and then
file. Okay.
File.
My computer. Okay, desktop. Here. This is a very interesting article. I'm curious what. It's confirmed we live in a simulation. Okay. And this guy makes an analogical metaphor between computers and the universe. And I can't explain all of the argument. You have to read it again. But the basic idea is that if you were living in a simulated environment, because of the rules that govern the environment, you would have to have a particular calculational constant which cannot be violated, which in our real universe is the speed of light. So he's basically making a direct argument saying the fact that we have in our real universe this constant, which is the speed of light, is very strong evidence that we actually live in a simulation. You might
Yeah, I
find this
think
article
he
interesting.
interprets it as the kind of limitation of the simulation hardware, I think.
That's right. That's right.
Yeah.
That's right. You've seen this article before?
Yeah. So I'm wondering, like, Google probably suggests it to both of us because we are living in a simulation within a simulation where Google decides what to feed us, right?
There you go. No, actually, I think I got this in Scientific American. It was one of the articles in the Scientific American email that I get every day.
Okay. Yeah, I think with me it was suggested by Google based on my searches. It pointed to that article in Scientific American.
Anyway, I just read it briefly, and it was, of all the arguments I've seen, this one actually made me go, I don't know how to counter that. Yeah. It's a very, very interesting argument. So the similar argument that occurred to me was the Planck's constant, right? The Planck's length as being the smallest resolution that you can actually go down to. So that felt to me like similar to the argument of the discrete universe, right?
Yeah, but in a way that only seems strange to us because we were taught things about continuous variables and infinity, which is also just one way of seeing reality, right? It might.
So you could take the point. So you could take the point of view that everything is actually discrete, and that mathematics, continuous mathematics, is just our approximation, which allows us to do some kind of convenient computations.
Yes, that's how I see it a bit.
But then when you have to go and actually simulate it, you have to go back to a discrete computer to do it again. So there's the irony.
Yeah.
Anyway, I think there's a lot to your approach of starting from a discrete representation that I really like, Louise. I'm very intrigued to see where you go with this. Yeah.
Cool.
I guess if we have nothing else, we've gone a little bit extra, so we should probably say bye. And
yeah, I think we are good to go. If anyone has any other question or comment?
Try to ask it before. Can you hear me now? Or?
Yes, we do.
Okay. I think it's a quick question, Uwe. I was just wondering if you shift for your complexity analysis, if you shift your block instead of using this fixed position there, you shift it, if the complexity would be too sensible to that shifting.
Good question. I think the more blocks I have, the less sensitive it would be to the shifting. But at some intermediate stage, it could be sensitive. But what I did is simply take the entire time series, split it once in the middle, then split these blocks, and I didn't test any other shifted versions of that.
Mm-hmm.
That's a great question.
So there's also still a lot to do in that context.
So if you shifted it by little increments and calculated, then you could get an uncertainty on your complexity graph, right? You get an entropy of the entropy of the entropy.
Don't go there.
You hit the limits of the simulation there.
But instead of getting a line, you would get a fuzzy line, right? But it would still be useful.
Mm-hmm.
because you'd be integrating out the effect of where you exactly put the block. That's very clever.
Thank you.
I was just
Uwe.
checking if I've the pictures. Yep, you're welcome. Thanks
Bye.
for listening.
Good night.
Thank you. Bye-bye. See you next time.
Stephanie, how's your summary going of the thesis?
Oh my gosh. Yeah, I just finished my conclusion now. So I have the introduction and the conclusion. And I finished today. So yeah, great news. And I'm just waiting Diego to solve some problems. I want him to first review it and then I will send it to you probably by Friday or something.
Uwe, before you sign off, I have some news for you.
Cool. Okay, looking forward to it.
I will show you 1 second.
Yeah.
I'm looking for the photograph. If I can find it quickly. If I can't, I will send it to you later. Ah, yes, here we go.
Oh, it's hard to see it.
You can't see it?
Is it a bicycle with
Oh, you have a bike. Oh, you have a folding bike.
The Brompton.
Oh, cool.
Because the bike you take around is a folding bike too, right?
Yeah, yeah.
Yeah, when I was in
Cool.
Amsterdam,
Very nice.
I think it was 15, 20 years ago when I went to Amsterdam, I saw somebody with a Brompton and I always wanted one. And so I finally broke down and got myself.
Finally, you got one.
Yep, I really love it. It's just
cool.
Oh, what's this?
Oh, this is one last picture. This is a few different series and using this complexity thing. And the discharge is the green here. It looks like the one I showed. But, you know, a sine wave, for example, has a completely different shape, or a random normal, you know, shape. So there is the possibility to distinguish different types of complex behavior, just to give you on the way home.
So you're closer to a tilted line, which sort of makes sense in a way.
Mm-hmm. So rather simple thing. Let's talk about it another time.
Yes, yes, absolutely. We need to revisit our discussions, so we'll get back to those.
Thank you, everyone.
Thanks, everybody. Bye.
Bye, guys.
Bye.
Yeah.